This is an example of a proposition that is correct and the proof is also correct. And what I'm going to do in this video is talk about all the features of it that make it correct. And in the videos after this, I'll talk about, you'll see the same proposition, but incorrect proofs, and I'll talk about why they're incorrect. All right, so let's begin. Now notice the domain here is the odd positive integers. Now in later videos, instead of saying the domain is odd positive integers, what we'll do is just say the domain is the integers, and we'll use an if-then statement. We'll say that if x and y are odd, then x plus y is even. But because this is proofs 1, and in proofs 1 we don't use, we're just trying to set the stage really. I'll give you something to work on and think about that'll help your mind wrap around these ideas so that you can add more complexity in proofs 2 and proofs 3. Okay. All right, so because of that, we're not going to use conditional statements in proofs 1. Okay, so in any case, you can see the proposition says for all x, for all y, x plus y is even. Okay, now this is saying for all x's that are in the domain, the odd positive integers, and all y's that are in the odd positive integers, if you add any two of them, that sum is even. Okay, so now the way that I go about reasoning through this is just an example of how to reason through this. In best case scenario is you'll develop your own ways of reasoning through these ideas. Okay, but this is how I do it. All right, so the first thing to notice, or the first thing to decide, is if the proposition itself is correct. So pretend that you don't know that the proposition is correct, and just think about how you would actually go about figuring this out. Okay, so what I would do is I would just try some examples and just try and see if those examples work. So in other words, pick some x in the domain, pick some y, add them together, see if they're even. All right, so let's try some. Let's say 3 plus 7. Okay, that's 10. All right, so 3 plus 7 is 10, 10's even. Okay, so it seemed to work there. Well, let's try some other ones. I don't know. 5 plus 9. Okay, that's 14. All right, that seemed to work. All right, how about some other bigger ones? I don't know. Let's see, 35 plus, I don't know, 25. Let's say 25. 25's odd. Let's see, what would that be? That would be 3, 4, 5, so that would be 60. 60 happens to be even. Okay, so it seems like it's true. All right. So I'm thinking that it's true. I'm thinking that the proposition is true. Okay, now let's try and decide if the proposition, or if the proof is correct. All right, so I'm going to erase these here. That's how. And in fact, like I said, the proof is correct. Okay, so the correct answer to this problem would be A. All right, now let's talk about the component. So let's talk about this proof, and I will talk about this proof and the components of it that make it correct. All right, so the first thing is that we state the assumptions. You state your assumptions. Okay, so the assumptions here are that X and Y are odd positive integers, so the assumptions are stated. In a proof, you always have to state your assumptions. Okay, so those were stated. All right. Now, so now think about this in a top-down sort of way. Let's say I just wrote down that the assumptions. First, I wrote down the assumptions that X is an arbitrary odd positive integer and that Y is an arbitrary odd positive integer. So think about what follows directly from those facts. Okay, well, if X is odd, that means that X has this form. If Y is odd, then that means that Y has that form. Now there's a key piece here, right? It's not just true that because X is odd, that X has that form. And it's not just true that if Y is odd, Y has this form. Right? There's a key piece there. And the key piece is that this n here has to be an integer. And that m here has to be an integer. Right? That's the piece that is really important. Even an odd only makes sense with integers. Okay, so now there I've clearly stated what the so I've said, okay, X is odd, Y is odd. Okay, what does that tell me? That tells me that X is 2n plus 1 for some integer n. That's a very important part. And that Y is 2m plus 1 for some integer m. Now I should note that we can't say that X is equal to 2n plus 1 and Y is equal to 2m plus 1 because that's too specific. That's saying that we're adding the same positive odd integer. Right? Think about this, right? If X equals 2n plus 1 and Y equals 2n plus 1, well, that means that X equals Y. Okay, that was kind of a weird little symbol there. That tells us, that's an arrow there, that tells us that X equals Y, right? But that's too specific. We're not saying that when you add the same odd positive integer to itself, you get an even, right? We're saying that, but we're also saying more. We're saying that when you add two odd positive integers that aren't even the same, that you get an even, right? So it's too specific to use the same variable n for both of them, right? So it's very important that we use different variables there. So 2m plus 1, 2n plus 1. Okay. And again, if any of this doesn't make sense, take note of the time in the video when I said it, and then you can ask a question in email or in Zoom office hours, and we can have a discussion about it. Okay, so the next thing is that, okay, so now from the fact that X is odd and Y is odd, it follows that X is 2n plus 1 for some integer n, Y is 2n plus 1 for some integer m. Well, now we're trying to say, now in the proof is about what happens when you add them, right? So let's add them. That's the point, right? So if we're talking about adding them, so that's why we add them. Okay, so X plus Y. Okay, what is X plus Y? X plus Y is X. X is 2n plus 1. y is 2m plus 1. Now we do some math. You can see to get that 2, right, that 2 is the 1 plus 1. Right, so those add together to give you a 2. So you have 2n plus 2m plus 2. And then now factor out the 2. Okay? So this really is the key part of the proof. And that is that x plus y is 2 times n plus m plus 1. Now, think about, remember, how do we know, let's see, even and odd is only defined for integers, right? And so to say that x plus y is even, it has to be 2 times some integer. So the question is now is, how do we know that n plus m plus 1 is some integer? Well, the reason why we know that is because we've defined n to be an integer and m to be an integer above, right? We absolutely must quantify where things live. So another way to say this is quantifying the variables. All variables must be quantified. We must say where they live. They live in the integers. This is very similar to declaring variables. You could even call them that. The variables have been declared. You must declare all variables in a Java class, right? If you don't define the variables, you get an error. This is exactly the same thing. Okay, because we've declared n to be an integer and m to be an integer, then we know that n plus m plus 1 is an integer. And so therefore we know that x plus y is 2 times some integer. So then it's even. Okay, so the next step in the proof is really just commenting on why we have satisfied the definition. Since n, m, and 1 are integers, and the sum of an integer is an integer, we know that n plus m plus 1 is an integer. Now, this little piece right here, the sum of integers is an integer. This is something that, as a math major would prove. If you're a math major, you'll prove this in some other class, probably, let's see, set theory, a class on set theory. You would prove this. But for the computer science majors, you're not going to have to prove that. And for this class, we will just assume that this is correct, that when you add integers, you get an integer. Okay, so this is an assumption for this class. When you add integers, you get an integer. When you subtract integers, you get an integer. When you multiply integers, you get an integer. Okay. All right, and so this next line, so x plus y equals 2 times n plus m plus 1, where n plus m plus 1 is an integer. That's just restating the definition of even. And then we conclude that x plus y is even. Notice that we end the proof with the end proof symbol. This is very similar to, let's see, when you write an if statement in Java, you start with one curly bracket, and then you end with another curly bracket, right? This is kind of like the end proof. This says end construct. This right here says end construct, very similar to end proof. This is like begin construct. When we write proof, we just mean this is where the proof begins. All right, so this is a correct proof. The answer is A. All right, I'll in the subsequent videos, you'll see that different pieces of this correct proof will be missing, and then I'll select the answers of B, why it's incorrect.